Hello, everyone. My name is Jeffrey Marshall-Milne, and today I'll be giving a presentation about the Poincare Conjecture. The first half will be history, the second half will be math. The story all starts with Henri Poincare, who published a foundational paper in topology, Analysis Situs, in 1895. This had the first printed definitions of a homeomorphism and of the fundamental group. He would follow this up with 5 supplements, and he ended the third supplement with the following conjecture, and I'm going to use John Milner's wording here. Every compact polyhedral manifold with the homology of an n-dimensional sphere is actually homeomorphic to an n-dimensional sphere. Now, if you don't understand some of the words here, don't worry, we'll go over all that later. He would go on to disprove his own conjecture in the 5th supplement of Analysis Situs by finding a counterexample, which is called the Poincare homology sphere today. So this led to the 5th and final supplement of Analysis Situs, culminating in what is known today as the Poincare conjecture. And this time he asked it as a question. What he asked was, if a compact 3-dimensional manifold has the property that every closed curve can be deformed to a point, does it follow that that manifold is homeomorphic to a sphere? So he actually never investigated this question further. And the more general statement that a closed n-manifold with the homotopy type of an n-sphere is homeomorphic to an n-sphere came to be known as the generalized Poincare conjecture. The first major revolution connected to the Poincare conjecture was John Milner's discovery of exotic spheres. So in 1956, he momentarily thought he'd found a counterexample to the Poincare conjecture in dimension 7, meaning a closed 7-manifold homotopic but not homeomorphic to the 7th sphere. But upon closer inspection, he realized it's actually not diffeomorphic to the 7th sphere, but it is homeomorphic. Until this point, diffeomorphism hadn't even been defined, since there was no clear example of 2 structures being homeomorphic but not diffeomorphic. So this led to the inception of differential topology, and he was awarded the 1962 Fields Medal. The first major progress on the Poincare conjecture was in 1960 when Stephen Smell proved it for dimensions 5 and up. He was awarded the 1966 Fields Medal, and this debunked a pretty widespread misconception that topology would get harder in higher dimensions. What's interesting is, although the generalized Poincare conjecture is a completely topological result, meaning dealing with continuous structures, he worked almost entirely in the smooth category, so with smooth structures without any corners intuitively. The next major result was Michael Friedman in 1982, who took care of the case for dimension 4, and he was awarded the 1986 Fields Medal. He describes his proof as it's starting the same as Smell's, but with a topological twist. And Milner describes his proof as the very opposite of analysis, relying on methods of very wild topological structures with no differentiability. So that's interesting because he's working very much in the topological category, whereas Smell's proof was almost completely in the smooth category. The Poincare conjecture was finally resolved in 2002 and 2003 by Grigori Perelman, who took care of the case for dimension 3. Now, I didn't talk about dimensions 0, 1, and 2, but those were already pretty well known before Poincare even made his conjecture. So his proof is described by Friedman as more like Beethoven's 9th than a conventional proof. So not many people actually know this proof, and the people who do know it seem to be very impressed by it. And Perelman was a very interesting character because he actually refused a Fields Medal and a $1 million prize for his achievement. For the rest of the presentation, I just want to give everyone a very good idea of what the Poincare conjecture is actually stating, and I'll give it a quick explanation as to why it's true in 2 dimensions at the end. So we're focusing on 2 dimensions because it's easier, and states that a simply connected compact surface without boundary is homeomorphic to the sphere. So let's go over what everything means here. We'll start with the word homeomorphic. And I'm not going to give a formal definition given our time limitations, but I'll give an example and sort of a layman's explanation. Consider this circle. If we were to shrink it, stretch it, or deform it, like in one of these pictures, that would be considered a homeomorphism. We could even twist it or knot it in 3-dimensional space. Everything on the left is a homeomorphism, and we say those shapes are homeomorphic to the circle. However, if we were to cut it like this here, or if we were to glue 2 points together or fill in the area which it defines in the plane, None of these actions would be homeomorphisms. So the basic idea is, just like in geometry, you consider something the same no matter how you rotate it or reflect it or translate it. In topology, yes, you consider it the same no matter how you rotate it, translate it, or reflect it, but even more so, you generalize this to consider it the same no matter how you twist it, shrink it, knot it. So that's the basic idea of homeomorphism. Okay, next, what is a compact surface without boundary? And I'm going to explain this with some examples. If you don't already know what compact means, I think the easiest definition would be a bounded subset of Rn, which contains all its limit points. So an example would be a closed disk. So this disk here, and we're including all the points on the circumference. So yes, this is compact, but is it without boundary? Well, I'll take this opportunity to explain exactly what that means. If you consider this yellow point, our surface has an open disk which contains it, so it's not a boundary point. But if you consider this purple point, there's no open disk in our surface which contains it, so this is a boundary point and our surface is not without boundary. We could, of course, just remove all the boundary points to get an open disk, and this would be without boundary, but it would no longer be compact because we lost all the limit points which were on the circumference. If we take the disjoint union of the two, this will be neither. An example of a surface which is both is a sphere. So of these four surfaces, the only one which is compact without boundary is the sphere. Moving on, what does it mean to be simply connected? That means path connected and all loops can be shrunk to a point. Once again, let's look at some examples. If you look at a sphere, yes, you can connect any 2 points with a path in the sphere, so it is path connected. And also any loop on the surface of the sphere can be shrunk to a point, so it also has this property. If you were to take the disjoint union of 2 spheres, yes, every loop can be shrunk to a point, but it's lost its path connectivity. If you look at a torus, then yes, it's path connected, but if you look at this loop going around the hole, you can't shrink it to a point within the bounds of the torus because it's being blocked by the hole, so it does not have this property. Take the disjoint union of a torus and a sphere, it has neither property. So of all these 4 surfaces here, the only one which is simply connected is the sphere. Okay, so now I'd like to quickly talk about why the Poincare conjecture is true in 2 dimensions, and this comes down to a much stronger theorem called the classification of surfaces. This theorem states that a path-connected compact surface without boundary is homeomorphic to one of the following. Either it's homeomorphic to a sphere, an n-hole torus, or a sphere with a finite number of crosscaps attached. Now I can't draw this category of surfaces as they don't embed in 3 dimensions, but I can explain to you how to attach crosscaps to a sphere. You start with your sphere, you cut out a disk, and then you glue antipodal points of the boundary together. Okay, if you wanted to add multiple crosscaps, you just cut out another hole and do the same thing again. Now, how does this imply the Poincare conjecture in 2 dimensions? Well, as we discussed earlier, this loop in the torus makes it so it's not simply connected, and no matter how many holes you have in your torus, you'll always have loops which can't be shrunk to a point. So all of the surfaces from this category are not simply connected. A similar argument here shows that all the surfaces from this category are not simply connected, meaning the only compact surface without boundary to be simply connected is the sphere, which proves the Poincare conjecture in 2 dimensions. I'm running overtime here, so I'm going to skip my summary, but I want to open up the question here and let you guys know that there's analogs of the Poincare conjecture for piecewise linear and smooth manifolds. And interestingly, the piecewise linear Poincare conjecture has been proven in every dimension aside from 4, and the smooth Poincare conjecture is actually false. So I thought that's very interesting, a good way to open up the topic a little bit for the end of this presentation. Here's my bibliography, and I hope everyone learned something useful. Thank you.